So let's continue with the current schedule, and that Bergin is going to give his fourth and final lecture on making a habitable world.
Okay. All right, so we want to make the world like the Earth, and so I'm going to draw a lot upon some of the topics that I have introduced throughout the week, and also the other speakers, not Mario though. Okay, so we need to have a silicate-rich world, and I'll talk a little bit about whether that's always the case. If you want to make a habitable world, we have this idea of the distance from the star, where water would be liquid on the surface, and that defines our current concept of the habitable zone. And I want to expand that a little bit to ask the question as to whether you have the materials that life uses, and furthermore, whether they are available on the surface of the planet. It is not clear whether Earth took the organics, say that meteorites supplied it, were supplied, or it sort of reshuffled things around via geochemistry, and then via other processes created the organics that life then took off with. We don't know that answer. So in a way, it's actually simpler to ask, what is the supply of hydrogen and oxygen? Actually, we know that that's water. Where does that come from? Where does the carbon come from? And where does the nitrogen come from? And how common is it to supply just the elements in a way in the bulk form? And so what we think is, we're pretty certain that H and O is in water, right? And the CNN most likely came in organics, although there are other possibilities, but this, based on meteorites, that's the best guess. All right, now, silicate-rich. Now, in the interstellar medium, all of the silicon, down to, it's certainly the 95%, maybe 99% level, is in the solid state as these particulate matters that absorb starlight and re-emit in the far infrared. And we also know that about half of the carbon is in the solid state as well. So these, what we mean by solid state, these are refractory materials that are harder to evaporate. Requires temperatures greater than, on the order of 1,000, 1,500 Kelvin. Okay, so they're hardier. Now, the carbonaceous component might be some form of hydrogenated amorphous carbon, so some carbon with some hydrogens arranged in a certain way, or some carbons and hydrogens arranged in a different way, so polycyclic aromatic carbons, right? Now, if we take at a basic level that the Earth is made of interstellar grains, which it is, it should be part carbon and part silicon. In fact, carbon is more abundant than silicon. Ergo, we should be on a carbon rock. But we're not. Okay, that's an interesting thing. Now, it also is true, however, that we only sample part of the Earth. We sample the surface. And there is some evidence that there is some lighter element than iron and nickel in the Earth's core. It could be carbon. It could be other things as well. That evidence comes from the transmission or propagation of seismic waves. So there's two flavors of seismic waves. There's sort of the direct waves that come radially outwards, and then the ones that sort of radial, that go out, the S waves that come out sort of like in concentric circles, working their way out. The direct waves, the P waves, propagate through both liquid and solid, whereas the S waves propagate only through the solids. So this is depth into the Earth, and this is the speed of the waves as they propagate through the Earth. So here's the P waves, they propagate all the time, and the S waves don't propagate, the speed goes down to 0 in the core. Now the interesting point is that from the speed of the wave, you can actually understand something about the pressure of the environment, and that can give you actually the density profile, or estimates of the density profile of the Earth. So what people do then is they have, this is the model density structure of the Earth, okay? And this is if you take iron and you put it at very high pressures, all right, in this case at room temperature, this is the density versus pressure that iron is when you put it at very high pressures. They take basically anvils, diamond anvils, and they press down on the iron, and then they measure these quantities. Now, if you extrapolate, this is at room temperature, if you put it at the core temperature, this is what the density pressure would look like for a pure iron, and if you put nickel in there, it would be something comparable. But there's a mismatch between the model from the seismic waves and what iron should be, and in fact, it's lower. So you estimate, or you infer, that there's something lighter than iron and nickel in the core of the Earth. And the candidates are hydrogen, carbon, oxygen, silicon, sulfur, and maybe even nitrogen. Okay, so now this is a plot where I'm trying to put everything together. It's a crazy plot, lots of stuff on here, and I'm just going to highlight and work through it a little bit. So this is taking carbon in various bodies in the Earth and elsewhere, and putting it relative to silicon. Now in astronomy, we generally put things relative to hydrogen, because that's the most abundant element. But if you want to talk about making Earths, what's the most abundant element? It's silicon. So I'm going to put everything relative to silicon. So here's the sun up here, okay? Now here is the Earth. The Earth is depleted in carbon. All right, there's the surface. This is some estimate of missing carbon over here. So the Earth is depleted in carbon relative to the sun. So what does that mean? That means that there was more carbon perhaps in the gas than in the rocks. Okay, but again, we have this problem that we don't know exactly the amount of carbon that might be sequestered in the Earth's core. So where do we go? Well, we go to meteorites. Here are meteorites. Okay, this is the most primitive form, the Ci. These are the carbonaceous chondrites, all of them. And we see that these are also depleted in carbon relative to silicon compared to what was available. Now, we know, let's go over to this side of the diagram. This is the interstellar medium, okay? Some of the carbon is in the gas, and some of the carbon is in the dust. All right, so the Earth should have been made of this plus silicate grains, but we see that there is this difference, right? So that here's the abundance. The Earth and meteorites should have about this amount of carbon inside of them, and they don't. So what does that mean? That means somewhere, or at some time during this process, you destroy carbon grains, and the process is planet formation. So at some phase, you destroy carbon grains, and that leaves you then with an Earth that's made of silicates. Now, there's some hints that this process was clearly active, but there's some hints that this process has either a radial or a time dependence to it. Because here's Comet Halley. Comet Halley, we had the Giotto spacecraft that visited it and actually got accurate measurements of both the volatile carbon, the carbon that came out, and also the carbon that was in the solid state. And it appeared to have almost the same amount of carbon that you have in the interstellar medium. All right, so whatever was going on, it was active in the solar system, and maybe it decayed with distance, or depending upon when you took the Halley-type comets and threw them out to where they are, it could have had a temporal dependence. Now, there's a lot of stuff out there if you look in the exoplanet literature, not a lot, but enough, suggesting that there might be carbon planets out there, pure carbon planets. And we actually have evidence that these planets don't exist, because we have a really neat method where we can actually get and see the abundances of rocks around other stars. Now, when all the great stuff that Jack showed, what we can get is we can get a size from Kepler, and we might be able to get a mass from RV, and we can estimate a density. And then we take that density and we guess at what different combinations of material might comprise that, and oftentimes you could get different combinations of things to give you the same density. You don't have a direct measurement of the abundances of the rocks that comprise that planet. But actually, we have a way of doing this, and that's using dead stars, white dwarfs. So So white dwarfs are, the sun is going to become a white dwarf. It's a floating ball of carbon in space. And some white dwarfs have been known for well over 100 years. In fact, it's likely that the first planetary system was detected around a white dwarf. We just didn't know it. These white dwarfs have metals in their atmosphere. So a white dwarf is a ball of carbon with a layer of hydrogen and helium. That layer of hydrogen and helium is very highly convective. All right, so anything that's on that surface should just be dredged right down, and you should, if there's iron supplied in some way to the surface of that star, it'll be dredged down and it'll be gone in a very short time scale. But yet they observe about 30% of these white dwarfs have polluted atmospheres. It's kind of neat. And then Spitzer came along and they found actually that these white dwarfs also have infrared excesses. They have a disk. All right, and so now we actually know where this stuff came from. Before they thought maybe it was the white dwarf plowing through space and gathering up interstellar medium material. But no, it has a disk. So you have a planet or asteroids or something, and they get close to the tidal radius, or through interactions, they get pushed to the tidal radius of the white dwarf, and it gets completely disrupted and supplied onto the surface of the planet. So it's an indirect way of measuring the abundances. So here are several of these white dwarfs, down sticky. We see lines of carbon, oxygen, aluminum, silicon, phosphorus, chromium, iron, nickel, all in this thing. Okay, so they also, from the abundance analysis, they infer that these rocks betray evidence of differentiation. So this is magnesium to silicon, iron to silicon. So magnesium and silicon, these are two things that track each other. All right, so they should be sort of mantle. And iron to silicon would be, core to mantle ratio, if you will. All right, so there's the sun, the Earth. Well, here's the crust, the outer crust of the Earth. Has very light. All right, and the mantle of the Earth is over here. Estimates, okay. Now, if we look at these white dwarfs, they're this point, this point, this point, this point, this point. All right, they're hydrogen white dwarfs, and the blue ones are helium-rich white dwarfs. We see that there's less dispersion for the magnesium to silicon ratio. That's comparable to mantle material, but wide dispersion in iron to silicon. So some white dwarfs have compositions similar to the moon, which we believe is made of earth mantle material. And some white dwarfs have compositions in iron to silicon comparable to Mercury, which we know is heavy metal rich. So that's telling you that there's evidence, indirect, that differentiation actually is occurring in other bodies. And remember we talked about the fact that this differentiation is due to 26 aluminum in the initial bodies of the solar system. That's actually taken as indication that 26 aluminum is likely supplied to many planet-forming systems as they form. Now let's talk about carbon. This is oxygen to silicon from a bunch of white dwarfs, carbon to silicon from a bunch of white dwarfs. Here's the interstellar dust carbon to silicon ratio. White dwarf, this is an upper limit this way, all down here, all down here. This is the Earth, and meteorites cluster around here. There's the sea ice. Okay, so all of the measurements that have been done, again, we're talking on the order of about tens. This number will get bigger as time goes on, are carbon depleted. So what does that mean? That tells us that whatever this process is that's occurring and has destroyed a lot of the carbon grains before we made planets, is active. It's just part of the process of planet formation. That's cool. So how can you do this? There's the best idea is you destroy the carbon grains and leave the silicates alone, is to oxidize the carbon. You just burn it. All right, we know that carbon burns. We do it ourselves. And this was suggested by Duchel et al. Using OH. Atomic O is something that I explored with Zhonglin Li. And I'll show you a little bit of how that works, or how that might work. So if this happens, you have to have hot gas, okay, and oxygen or OH. But if this will only destroy carbon, it leaves the silicon completely alone. It puts the carbon in the gas, mostly in the form of CO. And so you just have to ask, where could this be active? And the best guess for where it's active is on the surface of the disk, where it's hot, right? So we know when we looked before that the surface here is hot and the inner part of the disk is also hot. So they're the places where it could be hot enough to do this. The question is, can you put the dust into that area? So let's talk a little bit briefly and put together planet formation with this sort of erosion. You start in the beginning, you have a disk, well-mixed gas and dust, and I'm going to be able to destroy, I'll show you, the carbon grains on the surface of the disk. But the dust actually settles to the midplane, so it's gas drag, and pressure gradients leads to basically dust settling to a dust-rich midplane, okay? And that's where you make your planets. Now the thing that retards this process, that slows this down, is any turbulence in the disk. That can take smaller grains and loft them up to heights, larger heights. And bigger grains, they're harder to lift, but the small grains can get lifted to higher heights. All right? So this is a model by Dolman and Dominic. This is height, radius versus radius. These different colors are grains of different sizes. So you can stir grains up to different heights. Smaller grains higher, larger grains lower. Okay, so it's a question actually of time scales. Can I destroy these carbon grains if I take the small ones and I stir them up there? And how long do they stay up there at heights where they can be exposed to oxygen atoms before they go back down and destroyed? So we want to know something about the grain destruction time scale.
But, I know you don't like convection, but wouldn't convection also help this?
They would if it were active, yeah. But the gas is, because of the heating and the gradients, is thought to be convectively it's stable.
According to the standard theories, the hottest these grains are going to get is in the accretion shock when they enter the disk.
No.
Everything's going to get that depending on where it hits the disk.
Okay. So yesterday, which you weren't here for, I showed that in the disks themselves, the temperatures are not high enough to activate this. And you would never have deuterium fractionation in any materials in the solar system if all material passed through a hot phase. So you had to have hot and cold materials mixed together.
It depends where it hits the disk.
That's
If
correct.
it's the inner part of the disk.
That's right.
It heats immediately. If it's the outer part of the disk, it
That's
doesn't get
correct.
nearly as high.
It could get vaporized, but if it's dense enough, then you would still make the carbon grain. So you have to do this somehow in a way that's not equilibrium.
It's dense enough,
Yes.
you still make the carbon, but I thought you vaporize it,
Mm-hmm.
and then, since the solar nebula was an oxygen-rich environment, the carbon would be combined with the oxygen.
It might. It depends if it's kinetically, the so-called quote-unquote kinetic inhibition models.
Okay.
So if you read the Lauder's paper, one of the pass outwards is graphite, actually. And that doesn't happen.
Okay.
That doesn't happen. Yeah, so this could happen early, but then you still have to destroy the stuff that's provided late. And the other point is that the centrifugal radius where material is supplied by infall, that goes outward to something like, I think it's T cubed or something like that. So it goes out very, very fast. So only a very small amount of material is subject to this very high infall shocks. And most of that material goes into the star, actually, because it's close in. And so when you get out to 30 kilometers per second, or let's say, out to the Earth or beyond, the shocks, well, you get to 10 AU or whatever, the shock speeds actually are much less, and it's not clear right now whether those infall shocks actually do anything beyond mild heating of material. So I don't think that actually that's not as important as we had once thought, but the early phase is the least understood. Okay, so I take my carbon grains, and here I have a disk full of carbon grains, and you'll see once I let this go, this is from Dana Anderson, student of Jeff Blake, working with myself she's at Caltech, and I'll let it go again. And I basically destroy carbon grains very quickly, hundreds of years in the surface layers. So you just have to stir them up, okay? So here's a plot of time scales. Here's my stirring time scale. This is the destruction here. Or this is the destruction time scale. This is the stirring time scale. And where this is lower than this process actually is capable of being active. So in the first, over the, the inner 5 to 10 AU, you can destroy things, okay? This is going to depend upon whether turbulence is happening. It'll be distance and time dependent, but it can get rid of your carbon grains, even during periods, basically before the periods of planetesimal assembly. All right, so meteorites and the Earth are carbon poor. Carbon was in the gas, and I gave you one solution. The polluted white dwarf atmospheres provide a measurement of the bulk abundance of other solar planets, of extrasolar planets, and there is no evidence for carbon-rich planets. Now, maybe there's some way to stop this process from happening, but again, it's suggestive that there's an actual physics mechanism. So this is the plot I showed earlier. I'm going to move on to water now. That was carbon. Here's our lovely Earth. Now, we talked about the fact, I think David mentioned, that the Earth has a tiny amount of water. If you take the amount of water that we believe the Earth has and you put it in the same, the volume that it would occupy, you can see that the Earth actually has, a drop of water relatively on its surface. And that's an interesting statement. Okay. So we have some questions. Well, we talked about it's too hot at 1 EU. I think everybody got that point. And we believe the water came from planetesimal delivery. I'll motivate that a little bit more. But you saw the model from that. I want to talk a little bit also about where was water made. If it was made in the interstellar medium, almost completely, then all solar systems will probably be provided with abundant water, our forming solar systems, that is the disk. But if it's made in the disk itself, which is one possibility, so if you go back to this idea that everything, you take the meteorites, everything went through this hot phase, right, where everything was evaporated and then you reform it, okay? Now, if I were to do that, then I wouldn't get my deuterium enrichments. That's one point, all right? The other is, well, maybe that means if it's the disk itself that's doing it, that there could be different levels of collapse or different processes in the disk. We know that they have ultraviolet radiation, X-ray radiation, they have different amounts. So the physics of systems will actually be different. And maybe that suggests that there's a diversity of outcomes that you could make. Some systems may make abundant water, some systems may not. All right? So the basics of water. Here's our astronomical modes of detection. As I told you, it's this little dancing. And here is the water rotating. So as I was talking about, this is the vibrational modes of water being detected. Now this is Galileo turning around on its way out to Jupiter, taking a look at the Earth. So this is a spectrum. This lets you know that the Earth has water. That's cool. This is the spectrum of rotational emissions that water emits. And you can see that at different temperatures, you see different emissions. So what is this? So at very hot gas, there's more emission in the mid-infrared. Very cold gas, it goes out into the sub-millimeter, and in between it's like far infrared. And you can see that the portfolio of emission, you see this shape here, if you can detect it all, which we can't, but we can often detect several lines of water, allows you to estimate the temperature of the gas. This is the water chemistry. I worked through that before, and this is a confusogram anyways. I'll just tell you very quickly what happens. If you're in LTE, that is the forever and a day equilibrium chemistry, all free O will be converted to water. If you're very hot, you'll have tons of water. If you're cold, less than 400 K, that's not cold by interstellar standards, then you need ionization, and the chemistry is very inefficient. However, if you're in the solid state, all right, if the dust is less than 150 K, you can freeze out, and if it's less than 30 K, you can form it via surface chemistry. But you need hydrogen atoms to make the water, actually, and to make hydrogen atoms to make water, you need ionization to make the hydrogen atoms. Okay, so that's water. Now this is a movie that Avina Vanishok made showing how the main formation mechanisms of water occur, and this is the surface chemistry And I keep wanting to put a soundtrack to this, but I haven't yet. I was thinking of Sweet Child of Mine, but you know, you can put whatever music you want. So the white ones are hydrogen atoms. As you see, they move more rapidly because they're lighter, and the red, of course, is oxygen. So sometimes you make, that looks like that's an HO, I think there's another H there. Oh, there it came. So H2O2. And, you know, lots of fun stuff going. And, of course, this is very efficient. And then you make your water ice coated grain. A little party going on. All right, so that's the main way we think you make water. Now, if I have water in the gas, I've made it. How do I destroy it? Well, I can destroy it by ultraviolet photons. If it's cold, I could take the ionization and it's abundant, I may lower its abundance. If it's in the solid state, I can evaporate it. All right. If it's greater than 150 K, although this number is pressure dependent. If it's less than 150 K, you can still remove ices from the surface of grains via erosion, via ultraviolet photons hitting the surface, hitting the water molecule, putting it in a state that's dissociated from the grain, and it can pop off. So, what do we know about water? So this is in pre-stellar cores. This is before the star is born. This is a detection of water vapor in the gas. So this is the blue is water vapor. You can see it has a very interesting line profile, which actually tells you that the gas is infalling. There's a molecule tracing the center of the core. When we measure the abundance that we estimate from this, it's a fraction of the oxygen abundance. This is a tiny amount of water vapor. And we know that this is coming from dense gas because this line has a high dipole moment. This is a high dipole moment molecule, and it only emits from very dense gas. Here's a line of sight where there's a background star behind dense gas, and this is water ice. And based upon these measurements, we know that the ice abundance dominates. Ice has most of the free oxygen that's not in CO or in the solid state grains. So very little amounts of water. Water ice is formed during the pre-stellar stage, and based upon models, we believe, and laboratory work in spite of grain surface reactions. Now we have a star is born in the center, okay? We have a cold outer envelope, a warm inner parts near the star. There's a disk that's forming, and an outflow coming out that is perhaps shock heated. Okay, we have some expectations. We know from pre-stellar cores that this should be water vapor poor because the water is frozen on grain surfaces. If it's hot enough, maybe the inner parts of the envelope could evaporate water. The young disk, hard to detect, and the outflow, we believe, should be water vapor rich because it's easy to form it in warm gas. So let's talk about the outflow very quickly first. This is a young star. Here's water shown in that ejected material. Water is very abundant in outflowing material. And in fact, if I was going to tell you the story of water in the interstellar medium and not the story of water in planetary birth, the story of water in the interstellar medium is shocks. Shocks and then more shocks. It's very abundant in gas that has been accelerated and exposed to higher temperatures. Okay, we also detect organics in outflows as well. But this is not the story of an interstellar medium. This is the story of planet formation. This stuff is being thrown out into space. It's going to be destroyed by photons. So it's gone. It's going to go back to atoms and be part of the interstellar cycle of star and planet formation. All right, now let's get it from the core to the disk. All right. So the first place to look is close to the star in the envelope, and then we'll try to find water in a young disk. So this is what we saw, the so-called hot core, the hot gas in the envelope that's collapsing onto the star. This is very hard to do because this is what water looks like, as this really broad profile. It's dominated by shock emission. So we go to the lesser abundant isotopes, and we get this 5 sigma maybe detection. This took a lot of time. This, I think, was 40 hours or something, observation with the Herschel Space Observatory. This abundance is consistent with ice evaporation, but we don't know is whether this infalling material will make it to the disk or not, depending upon when the envelope dissipates. So we want to go to smaller scales, less than 100 AU. So for that we use interferometers. So I showed you the Herschel Space Observatory, that's unresolved. Now we're using the Plateau de Bourg here, or this might be the SMA or the Plateau de Bourg, I'm not certain. And this is ALMA. Okay? So now we have, 200 AU scales or 20 AU scales, and we find that water is indeed detected on very small scales. This abundance is well below 10 to the minus 4. So if the water is present in abundance, it's again mostly as ice. And this is the phase where the disk is being born. So what does that tell us? Well, that probably tells us that the accretion shock is not energetic enough to evaporate water ice. Okay? So people have looked at this theoretically, in particular Ruud Visser has taken models of disk formation and it looked at what happens chemically as material is supplied to the disk. And he finds that about 30% of the ice might be processed either by photons or something like that, and only a few percent becomes vaporized. All right? Most of the ice falls onto the disk without suffering a shock. And so most of the ice is in the models go into the disk unaltered. And that's consistent with the observations that I just showed you. If there was an accretion shock, and it's happening all the time, because infall is happening all the time, you should see very abundant water vapor, and we don't. Now the thing that operates counter to that is that if you put the water in the gas, it could very rapidly refreeze onto the grains. So it does depend upon timing. All right, so water is provided to the disk mostly as unaltered ice. We don't think that you get significant evaporation, but this is the least probe stage. But ALMA, as I showed you, can do this, and we're going to know this answer within the next few years.
Is this plot that you have
This one?
a function of entry point into the disk or later?
The whole evolution, including the entry point into the disk. So if you're infalling, that's right here. The infall stream could be coming along this way, right, where you could be exposed to photons along the outflow cavity wall as well. So it includes other things.
But is it where it hits the disk, or is it where it ends up after some other?
It also includes where it hits the disk, and that's on the basis of my statement that anything that hits close to it would have the accretion shock, but that goes into the star.
But do you have the material moving once it hits the disk in that plot?
No, actually it was a star formation problem, so he presumably was accreting and building up the star mass. He uses the Terabishu and Cassin, which is a very famous model. So yeah.
Okay, so it does include the viscosity and redistribution within the disk. Okay, thanks.
So let's go to the disk. All right. So what we know, and I talked about this a little bit yesterday, I'll give you the summary. We have actually pretty good demographics because there were lots of Spitzer spectra that were taken. So here are several T-Tauri stars. We see all this forest of lines, that's water. And the demographics are such that water is common if the disk is accreting onto the star. So that if there's energy generated from accretion from disk material onto the star, then we see water. The water is abundant, at least relative to CO. If we know the CO abundance, which we may or may not, it's coming from warm gas. And we don't find it when the disk starts to evolve and begin to have gaps and things. And you don't detect it as much towards A stars. That is, stars more massive than the sun. If we want to look for water in the outer parts of the disk where comets are forming, we have to go away from Spitzer. You know, Spitzer was the mid-infrared. I told you that was very hot water. You have to go to sub-millimeter far infrared to get the cold water. And so this is a detection towards the closest young star with a disk, TW Hydra, of water vapor in one of these cold lines. And it's present, but it's present in a very tenuous amount, very small amount of water, hinting that, again, the water is mostly as ice. And our demographics are such that we only have one detection in the 5 systems where we did a very deep integration, and lots of our shallower surveys did not detect this line. So we can try to detect water as ice in the disks, and the ice actually can emit in some cases. So here is a spectrum taking with ISO. There's other spectra now coming out from Herschel, and there's this bumps here, particularly this bump right here. That's due to crystalline ice. So about 20 to 50% of the cosmic O is seen as ices emitting in these systems, and Melissa McClure has some data from Herschel. In some cases, you can actually catch the disk. If the disk is flared and the starlight can pass through and provide a background, you can try to use that as a background source to detect ice. That's what was done here. Now, this particular plot has this thing here. That's a hydrated silicate that was claimed to be detected, and that is not apparently real in the newer data. So sadly, we see ices, but we don't see hydrated silicates. So what's going on with water? This is a model of the water vapor chemistry in the disk. And this is the close to the star, it's hot, and this is where you have lots of ions floating around, lots of chemistry that's being initiated, the high temperature chemistry, and that's where water is happening, or forming, all right? And here's the surface layer. Again, we have high temperature chemistry forming water in, this is 200 degrees Kelvin, very hot gas, but it's exposed to ultraviolet photons, so its abundance is being reduced. And then you go out here, and we have a very weak layer where the water is actually coming from this photodesorption. So when I showed you that detection of cold water, that line shouldn't be there, right? All the water should be frozen. You shouldn't detect it at all, unless there's some way to remove it from the grain. Okay, so what do we know? We know that we're seeing water. It's probably surface water because it's optically thick. That is, we're not seeing the midplane. Hot water is common, cold water is not. All right, and we've detected the ice reservoir as well. Now, talked about deuterium fractionation. All right, told you that it's powered at low temperature. All right, and that actually gives you an excess of deuterium atoms as well. So if I'm in the outer disk, all right, it's less than 50K in the outer parts of this, so I can fractionate. All right, if parts of the outer disk surface or in the midplane, it's difficult to fractionate. And if you have a high DH ratio in that gas, you're going to bring it down. Say evaporate water. Now here I go inside the inner disk, I evaporate all my water, the DH ratio is going to go down. All right, now why do I want to talk about this? The key point is that we know that the Earth has this deuterium enhancement, right? And if that deuterium enrichment could originate in 2 places. Either it's in the disk, the outer parts of the disk, because the conditions can do it, or it's the ISM. But you need ionization to power it. All right, so here is the plot sort of showing that again. There's the 10 to the minus 5, that's the universe value. And here's the Earth's water enhanced, okay? And here's our comets that are above the line, the Oort cloud comets, the Kuiper belt comets on the line, talked about that yesterday. And there's meteorites. Other thing on this plot is we can actually estimate the DH ratio in ices, evaporated ices in the interstellar medium, and we see that they're comparable, they're getting comparable to the level that we see in Oort cloud comets. A little bit higher perhaps. Now, the typical models of understanding the deuterium enrichments of the solar system is that you start with something that's like this high, comparable to the Oort cloud, and then you bring it in to the inner solar system and you have some sort of mixing. All right, so some of the water is altered, and the DDH ratio is lower. So if I take water and I bring it in, so this is radius in this plot, if I bring it in to where it's hot, I evaporate it, I lower the DDH ratio, and we know that some material goes in, some material goes out, angular momentum. You can sort of mix the disk together and maybe sort of homogenize it. So in this plot, these are models where they include the chemistry and the mixing and so on and so forth. So the typical model is that you start out with a high interstellar DDH ratio, and then you just mix it, or you bring it down via just hot temperature chemistry or reprocessing of the deuterium. All right. Now, if you include mixing, you can. That's this one right here. You can get this trend. So it's high in the outer solar system, and you can get down to the Earth's value. All right, so that's the way we do things. All right. But all of these things assume that you have ionization, and that also that the outer disk can potentially be the origin of the deuterium enrichments. But my student and I have been looking at the ionization environment quite a bit. This is the typical model where you have X-rays, there might be short-lived radionuclides, and also galactic cosmic rays. But our sun excludes galactic cosmic rays that are responsible for ionization because of the solar wind. Young stars have even more vigorous solar winds by orders of magnitude. Ergo, they should, in theory, potentially also exclude cosmic rays. So here's a model where we looked at it and scaled up the sun. And here's the ionization rate of H2. That's the main constituent. If I include cosmic rays and X-rays, and they're the things. And here, if ILSA, if you exclude the cosmic rays, you can see that the ionization rate is a lot lower. Okay, so if I do this, if the cosmic rays are not there, here's the engine of deuterium fractionation, H2D+. That's the beneficiary of cosmic ionization. And it is present, no doubt, in the outer parts of the disk where it's cold enough. Nothing, however, in the midplane. So if I take my water and get my DDH ratio, that's what's shown down here, it doesn't change at all. So this paper is going to come out in a month. I think actually in a couple weeks. And this tells us that likely at least 50% of the water that's in the solar system came from 1 million years before the star was born. The water is interstellar. Okay, so the water is formed in the ISM, provided the disk. It means it's unaltered. Right? It went into the disk and it was not subject to high temperature conditions for a long period of time. All right? It means that all solar systems start with abundant water. Now let's talk about carbon and nitrogen a little bit more. Okay, so we have to destroy the carbonaceous grains. We talked about that. If you're going to make an Earth, maybe you make the Earth out of the parts of that process that, it destroys some of the carbon grains, but not all of them. And the Earth has its carbon from that. We don't know. But there are other carbon carriers, and the other one is actually CO. All right? So if we look at the carbon budget, this is from the inner disk where we have the most information. All right? And this was from Klaus Pontoppidan. He compiled this for Protostars and Planets Review. All right, so let's forget about oxygen. Here's carbon. You can see that we have about 20 to 40% of the carbon is in CO that we see. All right, so we're missing some carbon. Maybe that's still in the solid states. We don't know. Now, I showed you yesterday that if we look in the outer parts of this, 10, 50, 100 AU, the CO abundance appears to be reduced. And in fact, it goes to something less volatile. That's this number here. It goes to some sort of organics. This is an illustration of that process. So this is the fraction of carbon in various things. This will be a time-dependent process, and you slowly erode the CO and you make other things. Same thing would happen to N2. All right. Now, what does this mean? And again, I'm trying to make an Earth, and as I told you in the beginning, I'm not going to have an answer for you. But what I can tell you is that whatever is going on with carbon, it probably is variable from system to system depending upon the processes that are going on. This particular process where you take the carbon out of CO and you stick it in organics organic ices, and that organic ices might be the precursors of meteoritic organics, perhaps. Depends upon the X-ray luminosity, the grain evolution, and also any sort of movement of material. All right, so what are these factors? If I have carbon in a solid state in ices, well, clearly the dust temperature is important. Any radial or vertical variation will depend on the spectral type of the star. UV radiation, there's geometric dilution as you go outwards, 1 over r squared. There will be a dependence on the accretion rate, and of course, stars more massive than the sun have more UV radiation. Stars are X-ray emitters, right? That depends. They actually have variable luminosities in the X-ray. They also flare. The grains are evolving, all right? So what does this mean? This all suggests, since it's radiation driven, whatever's screwing or messing with the carbon, it's going to be more active in the inner solar system than it is in the outer. That's clear. All right? That's also, and the other thing is, since that it may depend upon the luminosities of the stars, it suggests that there could be system-to-system diversity in what's going on with the carbon. All right, nitrogen. All right. Well, this is my last of the volatiles. This is the same plot, only now I'm doing nitrogen to silicon. So here we go again. There's the sun. Okay. Here's the Earth, way the heck down here. The Earth is even more depleted in nitrogen than it is in carbon. Here's carbonaceous chondrites. They are even more depleted in nitrogen than carbon is relative to the sun. Again, what does that mean? It means the nitrogen was in the gas. Probably is N2. Well, what about the interstellar medium? We actually don't see much nitrogen incorporated into the dust. If it's in the dust, it would be in the carbonaceous. We only have a limit. It's right here. So that's that line, and everything is below it. Okay, so ISM dust has very little N. Now, comet Halley, however, is above that. And it's inorganic, so it suggests that maybe the disk was making something somewhere. Go up here, meteorites, Earth, I also didn't talk about the white dwarfs. They are well below the solar and ISM limit. So they're nitrogen poor. This nitrogen is in organics, must have been in a volatile form. Very difficult to incorporate. So I looked at this a little bit more differently. I wanted to know what the interstellar medium was doing for nitrogen. And so what I was going to do is I'm going to try and put that on that plot here. What is the interstellar medium? If I think the nitrogen is coming from organics, what do interstellar medium chemistry do with nitrogen in organics? So I come back to this spectrum here. And I took those abundances with lots of, the best data that we have, and I added up all the forms of organic nitrogen that we detected and asked what is the abundance of organic nitrogen traced by interstellar medium. And then I found some way to estimate the silicon abundance. And for nitrogen, actually, it's mostly in HCN. The most abundant forms of carbon are methanol and other things. So back to this plot. This is the dense ISM organics. All right? Not much nitrogen is in organics, but it's the exact same region as we see for meteorites. It's not an answer, it's suggestive. Okay, and look at this. Comet Halley is way up here, and again, that's in some sort of organic material. So the interstellar medium is not making the stuff that's in Comet Halley. Interstellar dust is not making, somehow, the stuff that's in Comet Halley. The disk is doing something. All right? But the stuff that's in meteorites, perhaps, can come from the interstellar medium. So, nitrogen's depleted in solar system rocks, has to be in the gas. This actually is good news for an astronomer. It's in the gas, I can detect it. Try to detect it.
What if it's nitrogen, N2?
If it's N2, I can detect it if there's a source of ionization and make N2H+. So we're doing it. Okay. ISM organics are comparable to meteorites. Maybe they're the precursors. I don't know. Comet Halley is interesting. It's really interesting. What does this mean for planets? Actually, this would tell us that the N is with the carbon. And so you just follow the carbon. Or you can follow the nitrogen, and that tells you what the carbon's doing. That's also kind of cool. So here we are. This is our planet formation. You start with grains, you make planetesimals, you make planetary embryos, eventually make the Earth. Interesting little aside. There's this paper by Delphas and Pourmont where they use, the hafnium tungsten, in this case with thorium, to give an age for when Mars formed. Mars is thought to be younger than the Earth, which is consistent with it being a planetary embryo. It's about 2 million years. That's kind of cool. All right. Let's go back and talk about the solar system. This is a putative plot of the water content in the solar system, and in a way it also is a putative plot of potential carbon content. So this is the water mass fraction versus distance from the sun. So how is this constructed? Well, the N-type chondrites are believed to be linked to what are called E-type asteroids. So there's a gradient of asteroid in the asteroid belt as defined by their reflectivity, actually. So stuff in the outer parts of the asteroid belt are darker, thought to be more carbon rich. And stuff in the inner parts of the asteroid belt are lighter, thought to be more silicate rich. So they say N-type chondrites are linked to E-type asteroids. Ordinary chondrites linked to S-type, that's this one, and carbonaceous are C to D. And so then they plot the water content based upon the fraction of water that's in each of these different chondrites. You see there's the Earth. Okay, so we know there's a gradient in water. There's also a gradient in carbon and nitrogen content in the solar system. So we want to make the Earth. The best way we could think of doing it is planetesimal delivery. There's other ways. You may have captured gas from the solar nebula, but again, as David talked about, we generally believe that if that happened, this was perhaps lost. There's another model running around out there saying that it's not as well formed, that grains have hills and valleys. So you think your typical evaporation temperature is 150 K, but if I stick my molecule in the valley, maybe it's more tightly bound than if it's at the top of the hill. If these grains exist, if this actually happened, then the Earth should be swimming in water. That's perhaps the best argument against that. Now, we do know something about impacts from the moon. We all talked about this. This is the plot that I recreated because it was really fun of how they do the impacting. So we're counting the impact rate. So these are lunar craters greater than 1 kilometer per kilometer squared. And then you have the Apollo measurements. And this is a fit by one person who I got this from. And you can see that there's this sharp decay, and then there's Copernicus. So that this is, of course, a stochastic process. So, but there's this clear decay. These are the different eons that David talked about. So early life, hellish Earth, surface waters here. And then I also put on there where the estimates are for when life might have originated. So clearly there was still impacts going on when life was starting to take hold of the Earth, but the biggest impacts were during this phase. All right, these are our chemical fingerprints, right? And I'm going to go to the next one. So this is another chemical fingerprint is the nitrogen. And David talked about this. Here's the DDH, and also Jack. There's the DDH ratio. Again, so look at DDH. Here's the sun down here. Earth is the same as meteorites. The Jupiter family comets are similar to the Earth, but the other ones are not. The nitrogen isotopes is another way you might use as fingerprints. And the only one that's comparable in the nitrogen isotopes is the meteorites, because the Hartley 2, which has the same DDH ratio, has a higher level of 15 to 14. So if we want to use these things and use this to tell us something about whether water came from planetesimal delivery, that's pretty clear. It actually can rule out atmospheric capture because the DDH ratio of any water should have been lower than that, although atmospheric escape can lose the hydrogen and not the deuterium. And this other model for how you make water would not be fractionated. Okay, so planetesimal deliveries models really are consistent with most of our data right now. But again, it'd be better if we had good information at 1AU, which we're trying to get. Now, okay, I sort of kind of not really. left some carbon, hydrogen, nitrogen to make it into an Earth. But now I need to construct an Earth. Okay? And so I need the carbon and all these things to stay on the surface and not get sucked up in the core. All right? Water actually is solvent in the magma ocean, and it's not going to sink. As long as the oxygen's more abundant than the iron can't take away all the water. As long as the water comes in a decent enough abundance, it should stick around. All right, so what happens, you have an atmosphere, you have a magma ocean, and there could be some cycling, and you could lose some of your volatiles once they're supplied. And there's estimates for when the magma ocean solidified. We talked about core formation as one of those estimates. So this is a plot showing, the volatiles that dissolve in a magma ocean when it's got a massive atmosphere, and it depends on the pressure. And you can see you can stuff more of water and CO2 in your magma ocean if the pressures are higher. Now, how you do this and what happens, if you have your atmosphere, massive atmosphere, magma ocean, and then you're forming the core. It really depends upon the solubility and whether it's reduced or oxidizing, and David's the expert there. One example, and this is from my colleague Mark Harshman, if he makes some assumptions about what happens with carbon, you can stick a lot of carbon in the core, very little elsewhere. And this is the stuff that life is going to use to form your biosphere. Okay, so this needs to be understood if you're going to talk about whether worlds out there are habitable. Right? We need to understand whether the carbon, oxygen, nitrogen are going to stay on the surface. So this has to be explored, and of course the best place to understand that is to figure out our own planet. Another problem is that you can lose an atmosphere during impacts, and David talked about that. This is some work from Sarah Stort. So here you have the amount of atmosphere loss depending upon the specific impact energy, and you lose more you lose more of the atmosphere than when there's oceans. Turns out this works better if there's a liquid ocean. If there's liquids on the surface of the Earth, when the impact happens, it actually leads to a greater vaporization and more heating of the atmosphere and more blow off than if the ocean, liquid ocean, water, is not present. This is a number versus impact energy for various models of giant impacts. So let's see, this is the giant impacts are 10 to the 6. You can lose significant fractions of your atmospheric constituents, less so in the oceans. Here's the moon forming impact energy estimates. All right, so if you take one example, if I put most of the carbon in the core, water in the ocean, and nitrogen in the atmosphere, you would lose the nitrogen. Yes, sir?
Is that specific energy ratio to the mass of Earth or the mass of the impact?
I would assume it's ratio to the mass of the impact.
Why is that important?
Hmm?
Why is that so important?
Why is the mass of the impact important?
Well, no, why is the specific energy?
Oh, that I don't know. Yeah. This is just showing that there is the possibility that you can lose significant amount of volatiles via impacts early. Okay, so have I made a chemically habitable world? I have my oxygen as water, I have my CNN and organics, okay? I think we now know, it was always a big question in our community whether the water, the interstellar medium signature was preserved in comets, and it is. As long as we're right about that cosmic rays are excluded. And we have another paper coming out where we measure that in a disk, and we show that indeed the cosmic rays are not present in the midplane of the disk. So I think we're there. All right. We know or think that planetesimal delivery will happen, and ALMA is going to be the big actor here. We'll be able to provide information on ices when they evaporate in the sides of the snow line, and beyond the snow line, what's in the solids, there's the stuff in the gas. And if you can observe the stuff in the gas to infer what's in the solids. So this is, 10 years from now, I think we can make some more sincere statements about this problem, so you know where I'm going to be going. Now, the subsequent evolution, there's going to be a gradient of carbon, oxygen, and nitrogen content in the solar system, or forming solar systems, but we also know that things move around a lot. So it suggests that the supply might not be a problem, although we need to understand how these things are influenced by changes of the planetary system architecture. And then you can change things around by impact, losing volatiles, or putting things in the core. And how do these things depend upon the size of the planet? If you have a super Earth, is that going to be different? Is it going to be more differentiated? Take more stuff to the core? I don't know. So we need more information. The models with all the processes, they're pieces, they're different fields, but that's what astrobiology is all about, right? Is having this conversation. And we need more data from the early stages, ALMA, and we need more data in terms of terrestrial and giant planet atmospheres from elsewhere. We need more understanding of our own planet. We don't know the carbon content of the Earth's core. We don't know whether it's nitrogen or carbon or sulfur or silicon that is the light element in the core. So you try and tie all these things together, and maybe we can then truly understand whether life is possible on all these wonderful planets that we're seeing. And that's where I'll stop. Thanks.